Hello students, welcome to SuperProfs. The course which we are studying is Digital Electronics and this is lecture 12 on counters. So in the previous session we have discussed about the sequential circuits, basic sequential circuits like flip-flops, NAND gate flip-flop or NOR gate flip-flop. Then we have studied different more flip-flops like SR flip-flop, JK flip-flop, D flip-flop and T flip-flop. Then we have moved our discussion towards the registers and how it is able to store more number of bits than the only one bit which is stored in flip-flop. So by connecting 4 or more or n number of flip-flops, we are able to store more number of bits. We have seen its application also. Now we are taking the second part in the sequential circuits and this part is counters. So what are counters? What are different types of counters like up counter, down counter, the basic classification of counters like synchronous counter and asynchronous counter. We are going to see all these counters in this session. Okay, so let us first see what are the topics. For the counters, there would be three parts: synchronous counters, asynchronous counters and the state machines. So in synchronous counters and asynchronous counters, there would be a basic difference that we are going to see in the slides. In synchronous counters, the clock pulse is given simultaneously to all the flip-flops. So as in the registers, we are giving this clock pulse simultaneously to all the flip-flops. Similarly, in synchronous counters, we are giving all the clock pulse. We are giving clock pulse to all the flip-flops to count the clock pulses simultaneously. But in the asynchronous counters, we are not giving clock pulse simultaneously. We are applying a clock pulse at one flip-flop and the clock pulse for the next flip-flop would be the output of the previous flip-flop. Okay, then we are going to see the state machines. So let's start with the counters. Students, it's very important to understand this concept that is counters, because very much and very interesting questions are developed in this concept that is counters, and many good questions may occur in the gate exams. So I hope you would understand, you would make a proper notes of this counter session because there are many concepts regarding counters that is going to be studied. There are also many shortcuts available. So let's start with the introduction. This is the basic introduction of counters, in which we are going to see what is the definition of counter, what you mean by the mod number, what is the mod number for the counters, and how it is going to be used for frequency division. So let's start with the first point, that is counters are formed by sequential circuits. So the basic building block of counters are sequential circuit. Like sequential circuits, we are going to use flip-flops to make the counters. Okay, it counts the number of clock pulses applied to it. It means that what a counter counts. Counter counts the number of clock pulses that would be applied to it. Like if we are applying 3 clock pulses, then it would count as 1, 2 and 3 clock pulses, and so on. If we are making a But if we are having more number of clock pulses, then it would count that number of clock pulses. Okay, and by our modification and by our ease, we can change the mod number or the counting of clock pulses of the counter. So basically, it counts the number of clock pulses applied to it. The uses of counters are for counting its basic use, frequency division, and in timers. So we are going to see how it is used in frequency division and timers. So it is very important point. Third point is very important point. C. If n is the total number of states available, suppose we have n number of total states and small n represents the number of flip-flop. So we can develop a relation, that is n would be less than or equals to 2 raised to power n. Okay, to understand this this formula, we are taking one example. Suppose we have 3 flip-flops. So n would be 3. Then number of states or number of counts that would be available would be either equals to or would be less than 8. It means that using 3 flip-flops and that is connected in the counters, either we are able to count up to 8 clock pulses or less than that. So if it is a binary counter, it would count up to 8 pulses. But if we want a modified or customized counter, if we want to count only 5 to 6 or 7 pulses, we can also construct it. Okay, so the number of states that would be available would be less than or equals to 2 raised to power n. Okay, now the second point is mod number. What is meant by mod number? The mod number indicates the number of states in the counting sequence. So if we are having a counting sequence for 3 flip-flops, so there would be the mod number would be 8 because it is counting from 0 to 7, that is 8 clock pulses. So for n flip-flops, counter will have 2 to raised to power n different states, and this counter is known as mod 2 raised to power n counter. Okay, so if we have n flip-flops, the counter will have 2 raised to power n different states, because if we have 2 flip-flops, then there would be 4 input combinations. That's why there would be 2 raised to power 2, that is 4 different states, and this counter would be known as mod 2 raised to power n. That is for if there are 2 flip-flops, then it would be known as mod 4 counter. Okay. It also indicates the frequency division factor obtained from the last flip-flop. This point is very important, that it indicates the frequency division factor. Suppose we are giving a f frequency to a starting flip-flop. Okay, we are applying a clock pulse to the first flip-flop and it is having a frequency which is equals to f. Now the frequency that would be available at the output would be f by mod number. It means that it also indicates the frequency division factor obtained from the last flip-flop. Okay, so third point is also understood, second point is understood, and first point is understood. So fourth point is it would be capable of counting up to 2 raised to power n minus 1 before returning to 0. So to understand this point, if we are taking an example with n equals to 3, then it means mod would be 8. Okay, mod would be 8 and it would be able to count up to 0 to 7. Okay, so after reaching 7, it would again return to 0 and start counting from 0, 1, 2, 3, 4, 5, 6 and 7. Okay, so this is representing the mod number. So there are 2 node points available with us if applied input frequency is f. Okay, so if the applied input frequency which is given to one flip-flop is f, then output frequency from mod would be from mod n counter. Suppose we have a mod n counter will be f by n. So if the input frequency is given as f, then the output frequency would be f by n. Okay, where n represents the mod number of the counter. Okay, so n is representing the mod number of the counter. So it is also indicating the frequency division factor that we are getting after the last flip-flop. And if there are 2 cascaded counters with mod m and n, then the overall mod would be m into n. So this is another note point. Suppose there are 2 counters which are cascaded with each other, then we can say that the total mod would be the multiplication of individual mods, that is m into n, and the frequency division factor would be, if the input frequency is f, then the output frequency would be f upon m into n. So these are some points related to the introduction of counters. So this is the introduction of counters. So you can write these points. Then we are starting with our classification of counters. So write these points. Like first point is what is the definition, how it is formed, the number of states available. Second is mod number. So these 4 points are important, and these 2 note points, you can write the note points from a different pen or just highlighting these 2 points, because it would be very useful in problem solving session. So quickly write these points. Then we are going to see the 2 basic classifications of counters. So the types of counters. What is the basic classification of counters? First is synchronous counters, and second would be asynchronous counters. So first is synchronous counters and second is asynchronous counters. Why we are saying synchronous counters and asynchronous counters? Because here the clock pulse is given simultaneously to all the flip-flops. So clock pulse is given simultaneously. Okay, clock pulse is given simultaneously, due to which all the flip-flops will be activated, or we can say that the output from all the flip-flops would be available at the same time. Okay, similarly, if we are taking asynchronous counters, then we are not giving the clock pulse simultaneously to all the flip-flops. It means that if a flip-flop is given with clock pulse, then the clock pulse or the triggering for the next flip-flop would be available from the previous flip-flop's output. Okay, so this is synchronous counters and asynchronous counters. So you can write the definition also. For synchronous counters, clock pulses are given simultaneously. So the first counter or first synchronous counter which we are going to study is Johnson's ring counter, or we can say that it is a twisted ring counter. These are some special counters, these are some special synchronous counters that are constructed using a D flip-flop. So suppose we want to represent a Johnson rings counter. We are taking 4 flip-flops like this. So these are 4 flip-flops which are D flip-flops. This is A, B, C and D. So these are the outputs, these are the inputs that is available. Okay. So we are drawing the block diagram. So now we want to give the clock pulse. So this is we are doing the edge triggering of these flip-flops. So we are marking our triangle and we are doing the positive edge triggering. So this is our clock pulse. Okay. This is our clock pulse. So as we can see that all the clock pulses are given simultaneously to all the flip-flops. Now we are going to connect this complement output, or we are giving feedback to the first flip-flop by the complement of the last output of the last flip-flop. So we are connecting Q bar with D. Okay, and we are connecting this as this. So the output of A is connected to the input of B. The output of B is connected to the input of C, and the output of C is connected to the input of D, and the output or the complement output of D is connected as feedback to the input of A. So this is the basic diagram for Johnson's ring counter or twisted ring counter. The name also suggests that it is forming a ring, therefore it is known as Johnson's ring counter. And why it is said as twisted ring? Because we are not connecting from Q, we have twisted the ring from Q dash, that's why it is known as twisted ring counter. So you can draw this circuit or block diagram, then we are going to understand its functioning. Okay, by noting the mod values and what are the states available. So quickly make this point, then we are going to see its working. So suppose we have clock pulse like this. So using the tabular form, we are going to able to understand it quickly. So suppose this is clock pulse, this is QA, the output of D flip-flop A, that is first flip-flop, QB, the output QB, QC and QD. So initially suppose that all the flip-flops are at 0 0 0 0 state. So as every flip-flop is at 0 0 state, it means that QA is 0, QB is 0, QC is 0 and QD is also 0, but QT bar would be 1. So when first clock pulse would be available, this Q bar would go to DA and this here Q this D would come here. Okay, and when clock pulse is applied, due to the activation of all the flip-flops, that is due to the triggering of all the flip-flops, this D, that is the input D, would come as output 1. This input that was previously 0 would come here, this input that is 0 would come here, and this 0 would come here. So we are just making the table like this. So after first clock pulse, QA would become 1, this would become 0, this would become 0, this would become 0. So in the second clock pulse, as its complement is giving feedback to the first flip-flop, then it would again become 1. This would come here as 1, this would come here as 0, this would come as here as 0. Now after third clock pulse, again this one would come here as 1, this would come 1, this become 1, this becomes 0. Okay. After fourth clock pulse, this would become 1, this would become 1, this would become 1, this would become 1. After fifth clock pulse, this one as a complement is given, this one would go as a its complement, that is 0, would go as a feedback to the first flip-flop. Therefore after the fifth clock pulse, or after triggering the flip-flop fifth time, the QA output becomes 0, it would become 1, this would become 1 and this would become 1, because it would be shifted like this. Okay, so after 6th clock pulse, it would become 0, 0, this would be 1, 1. After 7th clock pulse, it would become here, what is 0, 0, 0, 1. And after 8th clock pulse, it would become 0, 0, 0, 0. So what was the state initially, we are able to get it finally. So we can see that it requires 8 clock pulses. This required 8 clock pulses to return to its initial state. Therefore, it is a mod 8 counter. Okay, this is a mod 8 counter. So the mod value will be 8. Okay, the mod value is given as 8. So if we want to write generally for Johnson's ring counter, U states that is the states that would be available would be 2 into n. So as n is 4 in this case, therefore the total used states would be 8, and unused states would be, what would be the unused states? Total states would be 2 raised to power n. So if they are 4 flip-flops, then using a binary counter we would be having 16 states, but in this Johnson's ring counter we are having only 8 states. So the unused states would be 2 raised to power dot 2 into n. Okay, so this is used states and unused states. So this point is also important. Now we are going to see the next important point. So if we write the decimal equivalent of these states, what we are getting, this is 8, this is 12, this is 14, this is 15, this is 7, this is 3, this is 1, and this is 0. So how it is giving used states from 8 to 12 to 14 to 15 to 7 to 3 to 1 to 0, then again from 8. Okay, so suppose if any error comes in these state, that is some unused state comes in the used state. Suppose we are having 2 or if we are having 2 as unused states, it means that if error comes at 2, so if this is the output of this Johnson's ring counter, then the next output would be, as its decimal binary equivalent is 0010, so if this output comes suddenly in the Johnson ring counter, then the next output would be 1001, that is 9. Okay, so the next state would be 9. So if 9 comes, then it becomes 10. If 10 comes, the next state would become 13. If 13 comes, the next state would become 6. If 6 comes, the next state would become 11. If 11 comes, the next state would become 5, and if 5 comes, the next state would become 2, and again if 2 comes, the next state would become 9. So we can see that all these states are not in the used states. So the used states were 8, 12, 14, 15, 7, 3, 1 and 0. But if suddenly if any unused state comes in the Johnson's ring counter, then it would not be able to return to its used state. So what is the meaning of this? That it is not a self-corrected counter. What it means, that if any error or if any unused state comes in this Johnson's ring counter, then it would continuously remain in the unused states. It will never come to the used states. Okay, so these are unused states. So these 3 points are very important. What is the table of representation of the Johnson's ring counter, and what is the mod value of this counter, what are the used states and unused states available in Johnson's ring counter, and why it is known as a non-self-corrected counter. Okay, so you can write these 3 points. Next we are going to see another type of synchronous counter. So these 3 points are very important for the Johnson's ring counter. Now we are going to see the ordinary ring counter. The feedback is given from the uncomplimentary output of the last flip-flop. What we have done in the Johnson's ring flip-flop, that the feedback was given from the complemented form. But in this flip-flop, we are not giving the complemented form of the output to the feedback. We are giving the uncomplimentary form, or we can say that the normal form that is available from the last flip-flop. So if this is A flip-flop, B, C and D. Okay, now we are marking the clock pulses. We are giving the clock pulses simultaneously. So these are the clock pulses available. So these are the clock pulses available with us, like this. So this is D, this is Q, this is D, this is Q, this is D, this is Q, and this is D, this is Q. So now we are making the connections like this, because the output of the previous flip-flop is connected to the input of the next flip-flop, and through what we are doing here, we are giving feedback from the normal form to this flip-flop. One point is very important, that at least one logic 1 should be available in this counter to count the values. One note point you can write here, that at least one logic 1 should be available to count the values. Okay, why it is necessary? Because suppose if we are having QA is 0, QB is 0, QC is 0 and QD is also 0. So on giving the clock pulse, as it is a data flip-flop, then always the output would remain 0, 0, 0, 0, and we are not able to count the clock pulses through the ordinary ring counter. So it is necessary to give at least one logic 1 to this counter. So we are marking clock pulse QA, QB, QC and QD. Okay, so what we are going to do, we are taking as one clock pulse as 1. So suppose this is 0, 0, 0, 1. Okay, now the second clock pulse would be 1, 0, 0, 0. The third clock pulse, after the third clock pulse, the output would be 0, 1, 0, 0. After the fourth clock pulse, the output would be 0, 0, 1, 0, because it is shifting towards right, and after the fifth clock pulse, it would again become 0, 0, 0, 1. So by how many clock pulses we are again getting our output? By 4 different states. So after the 4 different states, we are able to get our previous initial input, that is 0, 0, 0, 1. So the mod value or the number of states would be 4. So it is a mod 4 counter. Okay, so it would be having 4 different states available, that is 0, 0, 0, 1, 1, 0, 0, 0, 0, 1, 0, 0 and 0, 0, 1, 0, because after this state we are getting our initial state, that is 0, 0, 0, 1. So by using ordinary ring counter, we are able to count 4 clock pulses. So the use state available would be, if we are talking generally, the use states would be n, where n stands for number of flip-flops. So as we are using 4 flip-flops here, so the used states would be n and the unused states would be total number of states are 2 raised to power n minus n. So if we are, for this example, if we are having 4 used states, then we are having 12 unused states. So you can make all the nodes for ordinary ring counter, that is first the block diagram, then the note that one logic 1 at least should be available, and the tabular representation of the working. You can mark the arrows like this, so it would be more understandable. Okay, like this. And this is a mod 4 counter for this example, and generally the journal expression, the used states would be n and the unused states would be 2 raised to power n minus n. So quickly write these points, then we are going to see a self-started ring counter. The drawback of ordinary ring counter would be rectified in the self-started ring counter. So now we are going to see self-started ring counter. Self-started ring counter is constructed to remove the need for at least one logic, at least one logic 1 as an ordinary ring counter. Okay, so how we are going to remove this need? Let's draw its circuit or the block diagram. So we are taking again 4 flip-flops with us. These are the 4 flip-flops, A, B, C and D. Okay, so this is A flip-flop, B flip-flop, C flip-flop and D flip-flop. Now we are going to make its connection. This is clock pulse that is given to all the flip-flops simultaneously, because it is a synchronous counter, or we can say it is a special type of synchronous counter. Okay, so this is the clock pulse and this is D input outputs of all the flip-flops, like this, this, and this is the output. So what is the modification that we are going to do in this construction? We are passing the outputs of the 3 flip-flops, these 3 flip-flops, through a NOR gate. Okay, like this. We are passing the outputs of these 3 flip-flops through a NOR gate, and we are giving it as a feedback to the first flip-flop, that is A flip-flop. So in the ordinary flip-flop, we are not able to start our counter with QA, QB, QC, QD as 0, 0, 0, 0. But in this we can put 0, 0, 0, because when QA, QB and QC would be 0, 0, 0, this is 0, this is 0, this is 0 and this would be 0. Then the output of this would be 1. So we are able to get at least 1 through this this modification. That's why it is known as self-started ring counter, because we are not having any need to put at least 1 logic 1. It would be self-started and it would count all the values. Okay. So you can construct the self-started ring counter. This is the modification that is done. That is, we have passed QA, QB and QC through a NOR gate and given as a feedback to DA. Okay. So the note point that would be available that we have not connected QD, that is from we have not having the connection from QD. So it is a quite peculiar point. We are giving just feedback from QA, QB and QC, passing through a NOR gate and giving it to a DA. That is the input of the first flip-flop. So you can make the self-started ring counter. Then we are going to see some asynchronous inputs. What you mean by asynchronous inputs? So now we are going to discuss asynchronous inputs. So first of all, we should understand what is a asynchronous inputs. Asynchronous inputs can be applied at any time. So how it is different from synchronous inputs, and what would be the synchronous inputs? Suppose we are having a JK flip-flop. So the inputs J and K, if we are taking an example of JK flip-flop, then the inputs J and K are known as synchronous inputs because they should be applied simultaneously for the proper functioning of a JK flip-flop. Because if we are not applying these inputs simultaneously, we would be getting a different output. Okay, so for a JK flip-flop, J and K would be known as synchronous inputs, that we are giving these inputs simultaneously to a flip-flop. But but this is not the case with asynchronous inputs. In asynchronous inputs, they can be applied at any time, and its functioning or the output corresponding to that asynchronous input would be available. So there are two basic asynchronous inputs. First is preset and second is clear. Okay, so by preset we are able to make our output as logic 1, and by clear we are able to make our output clear, that is logic 0. So how we are going to represent it in a flip-flop? Suppose this is a flip-flop. Okay, this is S, R, Q and Q bar. Okay, these are the inputs, that is the synchronous inputs, and the outputs. Here we are giving preset and here we are giving clear. So what would be the truth table for this? This is preset, this is clear, and this is our output Q plus. Okay, so 0 0 0 1 1 0 and 1 1. So it is in active high mode, that is we are giving it is in a normal form. So when both preset and clear would be 0 0, then we are having the normal operation of the flip-flop, that is the output would be depending on the inputs that is given by S and R. So for 0 0 condition for preset and clear, we are having our normal operation of a flip-flop. But if clear is 1, then it means that the output will become 0 for all the flip-flops in the counter. That is, clear is activated as we have given logic 1 to the clear, and the output for this would be 0 at any point of time. when the asynchronous input is activated. If preset is activated, that is if preset is given 1 and the clear is deactivated, that is 0, then all the outputs available would become as logic 1. Similarly, if both the preset and clear would be activated, then we are taking it as a don't care condition, because we are not able to get our required or a unique output. So we are taking it as a don't care condition. This truth table corresponds to this block diagram. But if we are giving the active low inputs to the SR flip-flop in the form of preset and clear. Suppose we are giving a active low input for preset and active low input to a clear. Then what would be its truth table? It would be just opposite like this. So this is Q plus, this is preset and clear. So 0 0 0 1 1 0 and 1 1. So now the preset and clear would be activated for logic 0 input. As both the inputs are 0 0, then it would be a don't care condition. For preset equals to 0, it would be activated, then the output would be 1. For clear equals to 0, the clear would be activated, or the clear asynchronous input would be activated, and the output would become suddenly 0. And if both the preset and clear are 1 1, that is both are deactivated, it means then the normal functioning of the flip-flop would be having. So these are 2 points regarding the active low and active high inputs that is given to a normal flip-flop, and we have also understood why preset and clear are known as asynchronous inputs, because they can be applied at any time, any particular point of time, and the output would be available just after when we applied these inputs. And why we are saying J and K or S and R or D as asynchronous inputs? Because they are applied simultaneously for the proper functioning of the flip-flop. So you can write these points. Then we are going to start asynchronous counters. So in asynchronous counters, the clock pulse would be not applied simultaneously, and it would be different from synchronous counters. So first we are going to study how we are going to deal with, or how we are getting the states using a asynchronous counter. So initially first we are going to see a up counter, then we are constructing a table for down counter, and then we are going to design some counters with different mod values. Okay, so quickly write these points, then we are going to see asynchronous counters. Now let's start with asynchronous counters. In asynchronous counters, clock pulse is given to only one flip-flop, and the output of one flip-flop acts as a clock pulse for other flip-flops. So this is very important point from construction point of view and to understand its working. So to understand asynchronous counters, we are taking one example with two flip-flops. And using two flip-flops, we are going to understand what is the working of asynchronous counters. So one point that is very important, that asynchronous counters in this clock pulse is not given simultaneously. The one clock pulse is given to one flip-flop, and the output of that one flip-flop would be given as a clock pulse to other flip-flop. So in this we are going to use the toggle state of the flip-flops, because using the toggle state of the flip-flop we are able to count different clock pulses. So let us take an example. Instead of taking example using 2 flip-flops, because the answer would be very small, for that we take example using 3 flip-flops. Okay, so suppose we are having 3 flip-flops like this. This is A, this is B, and this is C. Okay, these are 3 flip-flops. If you want to take T flip-flop, you can take T flip-flop. If you want to take JK flip-flop, you can take JK flip-flop. But we have to use the toggle state. So to use toggle state for a JK flip-flop, we are going to apply J and K with logic 1, like this. This is connected to logic 1. For this J and K, the logic or the input applied is 1, so that we can have the toggle state of all the flip-flops. Okay, this is logic 1. Now we are going to connect the triggering or the clock pulse for all the flip-flops. So for the first flip-flop, suppose if we want to count the clock pulses, we have 3 flip-flops and it is representing the 3 bits. If it is MSB, so this is MSB and this is LSB. So we are applying the clock pulse to the LSB. Okay, and which clock pulse? We are doing the negative edge triggering of the flip-flops. Okay, this is the clock pulse applied to the C flip-flop, and we are using or we are triggering the flip-flops using negative edge triggering. Okay, and these are the outputs for the rest of the flip-flops, that is Q, Q and Q. Okay, so these are the outputs available, and now we are making the connections for rest of the clock pulses. For B, we are doing the triggering with the help of the output of C flip-flop. And for the A flip-flop, we are using the triggering or we are giving the clock pulse like this. That is connecting the output of the previous flip-flop to the clock pulse of the next flip-flop. So this is the connection that we are doing here. So to understand its working, we are simultaneously making the tabular form as well as the timing diagram. So what do you mean by negative edge triggering, students? In negative edge triggering, the flip-flop will be affected or the output of the flip-flop would be affected when the clock pulse transition would be taking place from 1 to 0. That means when the clock pulse is changing from 1 to 0, then only the flip-flop would be triggered and its output is going to be changed. So here I am drawing the clock pulse. Suppose this is our clock pulse, like this. This is our clock pulse available, and this would be the clock pulse for Q. First we are going to draw the clock pulse for QC, QB and QA. Simultaneously we are writing the clock pulse, or we are making the tabular form like QA, QB and QC. Okay, so as we are going to do negative edge triggering, then it means that on the falling edge the output of QC would be changed. Okay, so if QC is 0, then it would be toggled to one state. It would be toggled to the first state when it is falling, then when the clock pulse is at falling edge. So it would be 0, it would be become 1 at this point. Now again it would become 0 at this falling edge, this would become 1 at this falling edge, this would become 1 at this falling edge, that would become 0 at this falling edge. So this is the timing diagram for QC. So if we are taking just QC, so as J and K would be 1, it means it is in a toggle state, and when the C flip-flop is triggered using the clock pulse, the falling edge of the clock pulse would change the QC output from 0 1 1 0 0 1. Okay. Now the output or the B flip-flop would be activated on the falling edge of QC, because QC is given as the clock pulse to the B flip-flop. Okay, because as QC is the clock pulse given to the B flip-flop, it means on the falling edge of QC, the output of QB would be changed. Okay, so these are the falling edge available for QC, and for this QC we are able to draw QB. Okay, so suppose we are having QB as 0, so at this falling edge it would become from 0 to 1, and from at this falling edge it would again become, or it would be toggled from 1 to 0. So this is our timing diagram for QB, and it will go on like this. Okay, now the output of QA would be changed when QB would have a falling edge. That is, as the clock pulse for A is connected from QB, that is output QB, that is the previous flip-flop. Therefore, on changing on the falling edge of QB, the output of QA would be changed. So again I am using a different pen. So if QB is having falling edge at this point, then only the QA would change. So it would remain 0, and at this point it would become 1. Okay, so this is the timing diagram. You can understand the timing diagram like this. This is the timing diagram for up counter. Now we are going to see how we are making its tabular form. So as we have understood the timing diagram, we are able to represent our tabular form quickly. So this is the first clock pulse, second clock pulse, third clock pulse, fourth clock pulse, and fifth clock pulse, and it would go on like this. Okay, so let us mark the first clock pulse. So at 0th clock pulse, all the outputs are 0 0 0. Okay, after the first clock pulse, what would happen, that QC would be changed to 0 to 1. Okay, but as it is changing from 0 to 1, it means it is a rising edge, or it is positively triggering. Therefore, there would be no change in QB. It would remain 0 0, and as 0 there is no change in QB, there would be no change in QA. Okay, on the second clock pulse, 1 would be changed to 0. Okay, as this is the falling edge, it means this would trigger QB, and as this would trigger QB, the output of QB would be toggled, and it would become from 0 to 1. And now if we want to see for QA, we are looking for output QB. As this is a rising edge, that is, it is changing from 0 to 1, it means QA would not be triggered, and it would remain at 0 only. Now after the third clock pulse, QC would again become 0 to 1. As this is the rising edge, so the QB output would not be changed, and as QB is not changed, QA will also not change. Okay, for the fourth clock pulse, QC would again change from 1 to 0. Why QC is changing for every clock pulse? Because we have applied the clock or the input clock to the QC flip-flop. So at every falling edge of the clock pulse, the output of QC is changing, but QB is changing on the falling edge of QC and QA output is changing on the falling edge of QB. Okay, so for the fourth clock pulse, that is after the end of the fourth clock pulse, what would be the effect? That QC is changed from 1 to 0. It means it is a falling edge. Then the output of QB would be changed and it would become from 1 to 0. And as QB is also a falling edge, it means QA would also change and it would be toggled from 0 to 1. Why there is toggling happening? Because students, J and K inputs are applied at 1. So whenever the triggering would be available, the proper triggering is available, the output would be toggled. Okay, so after the fourth clock pulse, we are having QA as 1, QB as 0 and QC as 0. After the fifth clock pulse, 0 would be changed to 1 for QC, as this is the rising edge. It means it would not be changed, and as there is no change in QB, QA would also be not changed. Okay, now for 6th clock pulse, QC is changed from 1 to 0. As this is the falling edge, QB would be changed from 0 to 1, but as QB is the rising edge, that is, it is changing from 0 to 1. It means that QA would not be changed and it would remain at 1 only. Now for the 7th clock pulse, the QC would be changed from 0 to 1. As this is the rising edge, it would not be changed, it would remain as 1 only, and as it is remained at 1 only, there is no change in QB, therefore there would be no change in QA also. Okay, so this is after the 7th clock pulse. On the 8th clock pulse, what is the input? What would be the output? QC would be again changed from 1 to 0. As this is the falling edge and all the flip-flops are negatively triggered, negatively edge triggered, it means that QB would also be changed or toggled from 1 state to 0 state. And as this is also the falling edge or the negative edge triggering, this would again trigger QA flip-flop and it would be toggled to 0 from 1. So we are able to see that we are getting our initial stage from which we have started, because after the 0th clock pulse, the output was 0 0 0. So we can see that the number of states that is available using this counter, this is the up counter, so the number of states available are 8. So this is a mod 8 counter. This is also known as binary counter because the mod value, let me write the mod value. The mod value is equals to 8. Or we can say mod value can be derived from 2 raised to power n, where n is the number of flip-flops. So the number of flip-flops is 3. It means that the mod value would be 2 raised to power 3, that is 8. So it means that 8 states are available and we can count up to 8 clock pulses from this asynchronous up counter. So I hope you have understood clearly this up counter, because all the functionings of the rest of the counter, whether it is down counter or it is positively edge trigger up counter or it is whether positively edge triggered down counter, the same functioning would be happening here, but the variation would be in the clock pulses, because here as the clock pulse is given as negative edge triggered, in case it is positive edge triggered, then the change or the triggering would be happening at the positive edge. Okay, so the change would come here, that is at the positive edge, or we can say at the rising edge, where the clock pulse is changing from 0 to 1. Then only the different flip-flops would be triggered, and depending on the triggering there would be positively edge triggering the next output, or the output of the next flip-flop would be triggered or toggled only when the previous output is toggled from 0 to 1, or it is positively edge triggered. So this is negative edge triggered up counter. So you can write these points. Then I am going to give you a shortcut to understand or to learn how we are going to do this, or how we are quickly able to understand whether it is up counter or whether it is down counter only just by see the connection. So I would be giving the shortcut in the next slide, and we will understand it in our next session. Okay. So quickly write these points, then the shortcut would be available. In the next session, we are going to see designing flip-flops with different mod values, and then we are going to see some of the synchronous counters again, because previous synchronous counters were the special one. If we want to generate, or if we want to construct a simpler or the normal ordinary synchronous counter, we are going to see in the next session. And in the next session also we are going to understand the state machines. So I hope in the next session the counters subject or the topic would be completed, and in the next session we are going to see all the problems related to the counters, registers and the sequential circuits. Okay, so questions or the problem solving session is very important, students, for this topic. Okay, so I hope you have made these three things. First, the block diagram of our counter you can write in under the heading asynchronous counters to understand the working of asynchronous counters. Then you make the timing diagram, and simultaneously on the other side you can make the table or the tabular form tabular representation of up counter. So in normally questions we are not able to make the complete circuit or the timing diagram, so it is very important to understand only through the tabular form. So we have understood in the tabular form also that on the falling edge, that is when the transition is taking from 1 to 0, then only the next flip-flop would be triggered, because here we can see that when the transition is from 1 to 0, then only the output of the next flip-flop is changed from 0 to 1. But here 0 to 1 is the rising edge, so that's why the output of the next flip-flop is not changed. So this is the whole concept related to the up counters, and this is the way we can count the clock pulses using asynchronous counters. Okay, so the shortcut available is, you can write this shortcut, that is, if the counter is negative triggered, then up connected would be a up counter. What do you mean by up connected? If the connection or the triggering for the next flip-flop is taken from Q. In the previous flip-flop you can see that it is up connected, that is the input or the clock pulse for the next flip-flop is taken from the output Q, that is from up connected. So up connected would be up counter and down connected would be down counter. Down connected means if we are taking the clock pulse or the triggering for the next flip-flop from the Q bar. So this is down connected down counter. Similarly, if we want to construct from positive edge triggering, then up connection would give us down counter and down connection would give us up counter. So you can make this shortcut, and in the next session I would be explaining one of the counters so that it would be understandable to learn this formula, and you can also prove it. Okay, I hope you have written this shortcut. So this was the session, this was the session. In the next session we are going to see rest of the topics that is remain in the counters. Thank you.